All right, so in this second video here on the El Nino Southern Oscillation, we're going to consider the impacts of El Nino on large-scale weather patterns, dynamical theories, one in particular associated with explaining El Nino to La Nina transitions, as well as a simplified thermodynamic modeling that allows us to describe temperature anomalies in the upper ocean along the equator and how those can result from enhanced downwelling and/or upwelling. So let's get started. So here we're going to take a very simplified look at the atmospheric response to an El Nino-like forcing. So in this particular case, which is from a video put together by Dr. Matthew Barlow at UMass Lowell, there's a prescribed warming here that results from oceanic warming associated with El Nino that then facilitates enhanced latent heating, latent warming in the atmosphere associated with deep moist convection or thunderstorms. Associated with those are relatively high heights in the upper troposphere associated with the increase in thickness driven by that warming. And so we get anticyclonic rotation in the northern hemisphere and in the southern hemisphere, but it has opposite sign. And so that's what we see with these two different areas of black contours, just the opposing sign associated with that anticyclonic anomaly. So if we put this into motion here, for El Nino, we have this diabatic warming in the central equatorial Pacific that then facilitates this Rossby wave train that extends poleward and eastward in both hemispheres, directed toward the east with Coriolis deflection in both hemispheres, associated with a ridge, then a trough, and then a ridge, a trough, and then a ridge. And note that the colors are opposite in the southern hemisphere, given the opposite sense of rotation. Ridge, trough, and ridge. So we get this pattern that extends over many thousands of kilometers beyond the tropics in both the northern and the southern hemisphere in response to this diabatic warming that we see centered in the central equatorial Pacific Ocean. For instance, if we look along the coast of North America here, we see this red shading indicating anomalous anticyclonic flow associated with the response to the El Nino-like heating. We'll show in just a moment that that actually is a characteristic of El Nino events, warmer and drier than normal conditions along the Pacific Northwest coast into Canada and up toward Alaska. If we were to look at La Nina, we would need to shift this pattern off to the west because our warming would be maximized much further west within the ocean basin. And so if we focus on North America, for instance, that could cause this trough to be located further to the west, or this ridge to be located further to the west, because the entire pattern gets shifted back to the west. We see that in the tropical regions across the Pacific and the Atlantic Oceans in both the northern and southern hemispheres, we have enhanced cyclonic anomalies here in both basins and here in both basins, noting the difference in the colors. And so again, just emphasizing that the signal is strongest near where the warming associated with El Nino or La Nina, further back to the west, is concentrated, but it does dampen as you go further poleward and further eastward away from that warming source. So now we want to take a look at the large-scale impacts associated with El Nino events. We have Northern Hemisphere winter on the upper left, Northern Hemisphere summer on the lower left. And the different coloring indicates temperature anomalies and/or precipitation anomalies associated with each event. So blue alone indicates cool, green alone indicates wet, light blue is cool and dry, dark blue is cool and wet, peach or orange is warm, yellow is dry, brown is warm and dry, light green is warm and wet. And that's consistent between the two panels here. So the first thing that stands out for El Nino, and we'll take a look at this for La Nina momentarily, is that these impacts are concentrated in the equatorial Pacific extending to the Americas, with less impacts in Europe and Africa. They are concentrated in the wintertime hemisphere, especially here on the bottom depiction, which is for Southern Hemisphere winter. It's a little more expansive in Northern Hemisphere winter, but the signals are strongest and most reliable here in North America. So these signals, focusing here especially in Northern Hemisphere winter in northwestern North America, are broadly consistent with what we saw in the simplified model on the previous slide. There we showed enhanced anticyclonic flow associated with an El Nino-like heat forcing across the Pacific Northwest and northwestern North America. And correspondingly, we see warmer than normal conditions during the Northern Hemisphere winter in this region associated with El Nino. In the southern tier of the United States, into the Gulf of Mexico and northern Mexico, we see that it is relatively wet across the desert southwest and cool and wet from the Rio Grande Valley eastward to the eastern seaboard. And we see other assorted impacts in different regions across the globe, both for northern hemisphere winter and northern hemisphere summer. If we look at La Nina, we see the same general structure, that the impacts are maximized in the equatorial Pacific Ocean and into the Americas, with less in Europe and Africa and western portions of Asia. We see that the impacts are concentrated more in the wintertime hemisphere than they are in the summertime hemisphere, although again, it's not exclusively only in the wintertime hemisphere. These signs are broadly opposite of what we see for El Nino events, so focusing on North America here, the Pacific Northwest and northwestern North America tends to be cool, whereas during El Nino it tends to be warm. And then here across the southern tier of the United States, it tends to be both warm and dry during the Northern Hemisphere winter associated with La Nina. Here in 2022, we are coming out of a La Nina event, and the beginning of winter looked very much like this pattern. Very cool in the Pacific Northwest and very warm and dry along the Gulf Coast. We've had a pattern more recently that has not matched up with this, but it looks like as we head out of winter, we may revert more to this type of pattern. We shall see. And then here in the Northern Hemisphere summer, we see our impacts extending from the Indian and Asian monsoon region back into the equatorial Pacific and then down into the Southern Hemisphere here as well. So we can also see impacts of El Nino, and specifically the El Nino Southern Oscillation, on tropical cyclone activity, especially within the Western Hemisphere, so the Eastern North Pacific and the North Atlantic Ocean basins. So during El Nino, as we have depicted here at left, it is relatively warm and wet along the equator here in the equatorial central and eastern Pacific Ocean, and the associated anticyclone that is favored in the the tropical eastern Pacific Ocean generally is associated with less vertical wind shear. So you get a weaker gradient between high and low heights that facilitates less vertical wind shear. That's detrimental, vertical wind shear is, to tropical cyclone formation and in their intensity. And so when you have less shear, you tend to have more tropical cyclones. Whereas when you get out into the Atlantic basin, recall that extending east from the heating source associated with El Nino, you actually have lower than normal heights across the tropical Atlantic basin. These are associated with stronger vertical wind shear, and that also tends to facilitate sinking motion through the column that increases atmospheric stability. So the combination of those two things is detrimental for tropical cyclone activity. So you tend to see fewer storms here in the Atlantic and more in the eastern North Pacific during an El Nino event. Whereas the opposite holds true during a La Nina event. It's relatively cool and dry here in the equatorial eastern Pacific basin, and so consequently the response is more like what you see in the Atlantic during an El Nino event. You get lower than normal heights and stronger vertical wind shear accompanying that, which reduces tropical cyclone activity here in the eastern North Pacific basin. Whereas further removed from that heating associated with La Nina, you get less of an impact here into the Atlantic basin. And so consequently, you have weaker vertical wind shear and impacts to atmospheric stability than you see during El Nino. And so consequently, you get more tropical cyclone activity in the tropical North Atlantic basin. So now we want to take a look at a dynamical theory known as the delayed oscillator theory that can help us understand the development of El Nino and its transition over to a La Nina event. So in this theory for the El Nino Southern Oscillation, we start with what is known as a westerly wind burst. And there's specific criteria that can be used to define what this looks like, but for the context of this discussion, it is just a prolonged period of westerly trade winds, so thus near the surface over the central to eastern equatorial Pacific Ocean, that then helps to generate a combination of two oceanic equatorial waves. So these are similar in structure, but very different in terms of their propagation speed as compared to their atmospheric counterparts. We have an eastward propagating downwelling oceanic Kelvin wave, and we see that here in the warm colors. So this is downwelling because this anomaly associated with the Kelvin wave is associated with the enhanced westerly winds, which we demonstrated in our previous video is associated with anomalous downwelling that then leads to warmer than normal sea surface temperatures. So this warm coloring is no coincidence. It's meant to specifically indicate forcing that would lead to warmer near-surface ocean temperatures. We also get a slower moving and westward propagating upwelling oceanic n=1 equatorial Rossby wave. The atmospheric version of this is the cyclonic rotating anomalies associated with each hemisphere. And in fact, you have a very weak gyre associated with each of these circulatory features that is cyclonic in nature in the ocean as well. That cyclonic flow can be shown to result in upwelling. So the correspondence between the cool colors and generation of cool sea surface temperature anomalies is no coincidence here either. So these move relatively slowly, about 2 to 3 meters per second to the east for the Kelvin wave, and even less, 1 to 2 meters per second to the west for the equatorial Rossby wave. So it takes many months for these features to ultimately cross the Pacific Ocean, from center part to the west or to the east, and then vice versa. So here we take a look at 8 diagrams. After 25, 50, 75, 100, 125, 175, 225, and 275 days after the start of what we saw on the previous slide. So the first few images are pretty straightforward to track. We have our downwelling Kelvin wave that propagates to the east or to the right on these diagrams, and our upwelling oceanic n=1 equatorial Rossby wave propagating slowly to the west over the course of time. But note, as we get towards 75 days here, we start to see some interesting behavior that really emerges as we get to 100 and 125 days out. We started with an anomaly that was centered right along the equator, as we might expect for an equatorial Kelvin wave. However, what emerges at a later time is a structure that is symmetric across the equator and looks a lot more like an n=1 equatorial Rossby wave. And in fact, that's what happens. As these equatorial Kelvin waves propagate eastward and hit the coast of South America, they are reflected back as a downwelling or anticyclonic version of an oceanic n=1 equatorial Rossby wave. We don't quite see that for the cyclonic or upwelling n=1 equatorial Rossby wave over this first 100-day period. It's only about 125 days in and then thereafter that you start to see that. So as that upwelling n=1 equatorial Rossby wave hits the coasts of Asia, Indonesia, the maritime continent, and Australia, it's reflected back as an upwelling oceanic Kelvin wave. So the two flip places. They both remain upwelling or downwelling, but they change their nature. Kelvin to equatorial Rossby to Kelvin. And so these reflected waves then propagate the Kelvin wave eastward, the equatorial Rossby wave westward over the course of time. And so through the first 100 days, even through the first 125 to 175 days, this combination of waves are resulting in an El Nino ocean state. Net accumulated cooling in the western Pacific and warming in the eastern and central Pacific basin. But then as you get to 225 and 275 days out, the eastward propagating upwelling Kelvin wave overtakes the westward propagating downwelling equatorial Rossby wave. And so you start to see this cooling develop along the equator toward the coast of South America over the course of the next 50 to 100 days. And likewise, this warming associated with the downwelling equatorial Rossby wave progresses further to the west as you go forward through time. If you were to continue this process out even further, you'd get reflection of those waves back again. So you'd get this periodicity from one wave type to the other that then results in periodicity between El Nino and La Nina. However, this doesn't quite match observations. There's a lot of changing of these wave structures that takes place as you go from one event to the next, or even within a given event. And so this remains perhaps an incomplete theory for describing El Nino. Truth be told, we don't have a great theory as of yet that helps us fully understand the quasi-oscillatory nature of El Nino and its Southern Oscillation atmospheric component. So from here, we want to wrap up by looking at a simplified ocean atmosphere model. And this specifically is an equation. So really, we can call any equation a model, but we'll view this in the context of a model here that describes how surface ocean temperature anomalies evolve in time. So we're going to refer to these surface ocean temperature anomalies as T prime, T for temperature and prime for an anomaly or a departure from average. Temporal evolution means we're going to look at how that changes in time. So here on the left-hand side of this equation, that's what we're looking at. We have the partial derivative with respect to time, or T, of the surface ocean temperature anomaly, T prime. So this is going to be a local change of the surface ocean temperature anomaly. If you don't have El Nino or La Nina, that temperature anomaly should be 0. For El Nino, you would expect this to be positive if you're applying it in the central or eastern equatorial Pacific. You would want to warm the sea surface temperature and thus create a positive anomaly. And the inverse would be true for La Nina in the central and eastern equatorial Pacific Ocean. But we see that we have 5 terms on the right-hand side of this equation. So let's take a step through each one of these in turn. So this first right-hand side term here looks a lot like an advection term. You have a velocity dotted into the gradient of some quantity here. So this velocity, u sub 1 here, is the surface ocean current and its velocity. So you're looking at an east to west ocean current, and this is positive for an ocean current that is directed toward the east. Here we have t with a bar over top of it and t with a prime here. So you can take the temperature, or any variable for that matter, and write it as the sum of a mean and an anomaly. And that's what we have here, a mean temperature and an anomalous temperature. And this surface ocean current that we have depicted here is formally the anomalous version of this. So this is an anomalous ocean current, however it is created, advecting the total temperature, both the mean and the anomalous component. If we go to the second right-hand side term here, this also is an advection term, but it's a little bit different in that the ocean current is now the mean ocean current, or the average one, given by this overbar here. And the temperature is now only the anomalous temperature, given by T prime here. So this is the zonal advection, so east to west direction, of the anomalous temperature by the mean ocean current. Our third term is pretty long that we see here. And if we really squinted at this, we'd see that this is very much an advection term as well. Here, this T sub z defines the upper ocean vertical temperature gradient. It's really just the partial derivative of temperature with respect to height. And so if temperature increases going up as it does in the climatological sense, this term is positive. We have W sub s here, and this is the upper ocean's vertical velocity. And just like in the atmosphere, up is positive, including within the ocean. We have this M operator in front of these two terms here. This M operator means that whatever is inside of the parentheses is 0 if that quantity is less than or equal to 0. But if it's greater than 0, it's whatever the quantity is here. So for instance, m of 1 would be 1, but m of -1 would be 0. This overall is the climatological or the average temperature gradient multiplied by this departure in the vertical velocity. Specifically, you're looking at the total vertical velocity and just the mean or the climatological vertical velocity. Because of this M operator, we can't just have W sub S prime here, so it's not quite that, but we'll take a look at this in a little bit more detail shortly. This next term, term E here, looks similar to term D, but it's a little bit simpler in that we only have that first M term operating on the total, so the mean plus the climatological vertical velocity in the upper ocean. And here we're looking at the anomalous vertical temperature gradient. So how does that temperature difference with height vary from what it typically would look like? And then finally, this term F here is just included to balance the model. It has no physical meaning in our context. We call this a parameterized ocean cooling to ensure that we don't just run away into an El Nino or into a La Nina state. We want to create something that is quasi-steady or quasi-consistent over time. So if we perform a scale analysis on that equation on the previous slide, we'd find that term D, the anomalous upwelling term, is the primary driver of upper ocean temperature changes. And so I've rewritten that equation here, only containing the left-hand side, term A, and then term D, this anomalous upwelling term. So this term again is the vertical temperature gradient operating in the climatological sense multiplied by this difference in vertical velocity between the total vertical velocity and the climatological vertical velocity. So let's take a look at each of these terms here. We know that ocean temperature increases going upward as you get closer toward the sun within the ocean. And so this term here, T sub z bar, is positive. It's always positive. We have a leading negative sign here, so that means if we want warming, if we want the left-hand side to be positive, this term in the brackets here has to be negative for the sign to work out that way. So how can that happen? That can only happen when this first term inside of the brackets is less than the second term inside of the brackets. So that means that W sub S prime, well, let's take a step back then for just a moment. If we're focusing on the central and eastern equatorial Pacific Ocean, we typically have easterly trade winds that are associated with upwelling of relatively cold ocean waters. And so those easterly trade winds drive this climatological upper ocean vertical velocity that is directed upward. And so consequently, this M term ends up being just W sub S bar because it is positive. Here we have a positive plus an anomalous component here. So in order for this left-hand side term to become smaller than this second term here, this W sub S prime has to be negative, leading this whole M term to either be less than this M term or to be 0 ultimately, if this is so substantially negative, implying anomalous downwelling as to facilitate downward directed vertical velocity in the ocean. And so consequently, to get this whole term to be positive, with this leading negative and this term being positive, M of W sub S bar plus W sub S prime has to be negative, or at least less than M of W sub S bar, and that occurs only when W sub S prime is negative. So that helps us demonstrate that anomalous downwelling or a weakened upwelling in the overall sense is what is responsible for leading to warmer than normal ocean conditions associated with El Nino within this framework. So that closes our discussion of the El Nino Southern Oscillation. We'll move on from here to look at the Madden-Julian Oscillation, a shorter time scale but no less important mode of variability within the equatorial regions and beyond. But for now, that's all for El Nino.